Every time your smartphone or DSLR snaps into sharp focus, it relies on a highly calculated stack of glass. Over the next 6 minutes, you will take on the role of an optical engineer, learning to calculate lens power and eliminate the distortions that ruin a shot. Grab a calculator and a piece of paper. You will need them to follow the math behind these light-bending equations. Mastering these equations gives you direct control over where a focal point falls, preventing it from landing blindly in front of or behind your sensor. To start our design, we must distinguish between the two primary lens shapes, convex and concave. Convex lenses force light rays to converge. Concave lenses cause light to diverge. We measure this ability using the power formula, P equals 1 over focal length. Crucially, focal length must be in meters. A 0.5 meter convex lens gives a power of +2 diopters. Once you calculate the power of a single lens, you can predict how multiple pieces of glass will behave when stacked together. Modern cameras rarely use a single lens. Instead, they utilize a series of glass elements working in tandem. To find the total power of a stack, we use the combination formula. P total equals P1 plus P2. Stacking our +2 diopter convex lens with a -1 diopter concave lens leaves us with a total system power of +1 diopter. This means our entire two-lens system now behaves as if it were a single lens with a focal length of exactly 1 meter. This combination allows for precise control. While the convex lens pulls light in sharply, the concave lens spreads it just enough to land flat and focused across the entire digital sensor. Manipulating these opposing elements allows engineers to achieve sharp focus within a standard camera body. Even with a perfect mathematical plan, your photos will suffer if you use low-quality physical materials. One way to improve a design is by using high refractive index glass. These materials bend light more aggressively, allowing lenses to be much thinner while maintaining the same optical power. We also apply anti-reflective coatings. These reduce light bounce, ensuring more light passes through the glass to hit the sensor, resulting in a brighter image. Without these material considerations, your system will produce visible optical distortions. The first is chromatic aberration. This appears as red or blue color fringing around objects because different light wavelengths focus at slightly different distances. The second is spherical aberration. This happens when light hitting the edges of a lens focuses at a different point than light hitting the center, causing the borders of your photo to look blurred and stretched. By using our calculated +2 and -1 diopter stack with coated high refractive glass, we neutralize both the color fringing and the edge blur. Professional imaging results from balancing these mathematical focus points with the science of the glass itself. You have now drafted a complete lens system worksheet, from the basic power formula to final material selection. We identified lens shapes, converted focal lengths into diopters, and stacked opposing powers to achieve a clean focus on the sensor. Try this on your own. If you have a pair of eyeglasses or a magnifying glass, check the prescription in diopters and reverse the calculation to find its focal length in meters. Mastering these calculations and material constraints allows you to predict how light will behave in everything from a simple magnifying glass to a complex multi-lens camera.